On question 8, we have to restrict the domain on this question. And if you were here yesterday, we talked about this, but some of you weren't, so that's why I'm addressing this. We have to restrict the domain on this problem in order to do the inverse. And again, that doesn't stop us from doing the inverse. Please hear me say that actually restricting the domain does not stop us from doing the math, but it just means our answer is not 100% accurate. So, what you have to remember is that the reason I restrict the domain is because my function does not pass the horizontal line test. Like if I were to draw a horizontal line, it would touch the graph more than once, so that's what makes the inverse not a function. But if I were only looking at half of the function, like not this part here that I'm marking out, if I were only looking at that right half, I would be okay. And that's where the idea of restricting the domain comes in, is that I only want to see half the graph. Well, that half of the graph starts at what point? At 1. So that would be, and that starts at the vertex. So my restriction in this case would be x's that are greater than or equal to 1. Normally it's 0 because our vertex is on the y-axis. It's wherever your vertex is. That's where your restriction starts. Okay? Wherever your vertex is, wherever your line of symmetry is, that's where your restriction starts because you only want to see the right half of that graph. Tell me what you know about inverses. Okay. What else do you know about them? Like, what can you tell me about their graphs? Reflection over, yes, it's over y equals x. So wherever y equals x, so it's just some line that looks like this, roughly. They are reflected across that line, so it would be somewhere over here. It would do that, roughly, give or take. What do you know about their domains and ranges? Tell me what you know about your x's and your y's. Yes. What else do you know? What's the very first thing you do when you find the inverse? You flip them because in the inverse, the x's and the y's are flipped. So what happens with your domains and ranges? They're flipped. I know, right? Yeah, to find the inverse, the x's and y's are just inverted. They're flipped. Okay. Any other questions on the review? So, problem 11. I think the thing that freaked you out on problem 11 was this 5 here. Okay, so move it. You don't need it there. How do you move it? Okay. So now my problem would be x minus 5 equals, and I'm going to rewrite that 3x minus 11 to the 1/2 as square root of 3x minus 11. Does the problem look much better now? Okay, so what do you do? Okay, so you square both sides. And when you square x minus 5, remember that is not x squared. Don't write this. That is not x squared plus 25. You write that, all you did was fluh. We don't fluh, we FOIL. And you wonder why I keep saying this is because people keep doing this. I only address issues that I see. So then this would really be 2x minus 5s. Not a 2, the number 2, like the quantity 2 of these. Equals 3x minus 11, because when you square a square root, they cancel each other out. And then I FOIL x minus 5 times x minus 5. I'm not actually going to FOIL that because I think that you know how to FOIL well. I'm just going to tell you that it's x squared minus 10x plus 25 equals 3x minus 11. And I promise if you went through the whole process and FOILed every bit of that, first, outside, inside, last, and then combined your like terms, that's what you would end up with, is x squared minus 10x plus 25. So what kind of problem is this right here?
This is
a gross one? It's a quadratic. So we're either going to factor or use the quadratic formula. But either way, I have to make sure that I have everything on one side. Because if it's a quadratic, I have to get it to equal 0 before I can do any math at all. So that means I need to move the 3x over. So I'm going to subtract 3x from both sides. And I'm going to add 11. I'm going to do those in the same step because I like to save room. You can do them in two separate steps if you want to. It's fine. X squared minus 13x plus 36 equals 0. And that's what I need. Anytime I have a quadratic, I have to get it to equal 0. So what are your options at this point once you've got it set up like this? Factor or? Okay, can we factor this problem? Yes. Okay, so when we factor this, we need to make our t-chart. What's my product need to be? 36 is my product, and then my sum would be negative 13. Okay, so what multiplies to give me 36 and adds to give me negative 13? Yes, if both of them are negative, not just one, both. Negative 4 times negative 9. If, and this is something that y'all keep messing up on, and this is why I didn't address this at the very beginning of the school year like this. If and only if this number right here is a 1, if that coefficient is a 1, you can directly go into your factors. If that number is not a 1, that does not work. If that number is not a 1, you have to rewrite it as 4 terms and then group and factor. But if that number is a 1, you can just skip a step because your factors are going to be x minus 4 and x minus 9. And this still equals 0. So now I have two factors that equal 0. And the zero product property tells me that if I multiply two things and I get 0, then one of those two things must equal 0. So I set them both equal to 0. So if the first one, x minus 4, is set equal to 0, what is the x value there? 4. So one of my answers is 4. Then I do the same thing with the other one. I have x minus 9. I'm going to set that equal to 0. And then I get for my second answer, x equals, okay. What do you do now that you have your answers?
Put it back into the original form.
Plug them back in. How do you know if it's an answer or not an answer?
They don't equal.
Yes, if the left side equals the right side, that means that it's an answer. If the left side doesn't equal the right side, what does that mean? Yes, it's extraneous. That's our vocabulary word for that. Like it's an extra answer that didn't actually work out. I believe one of these is extraneous. I think 4 was extraneous. Okay, so 9 worked out, 4 was extraneous. You would need to prove that, of course, but 4 would be our extraneous answer. And you would need to write that, okay? You need to include that it's an extraneous solution, but if the question just asked you, said, hey, what is your solution to this problem? Like it didn't ask for extraneous, it said, what is your solution? Would you have one answer or two answers for this? Just one, because you actually only have one real answer to this. This one is your actual solution. So if it asks you, what is the solution? You're only giving me 9, okay? You are only giving me 9 because that's the only solution. But sometimes it's going to ask you, what's the extraneous solution? You have to give that one. Sometimes it asks for both, and it's going to specify, like in your answer, it may say, x equals 9 is a solution and x equals 4 is extraneous. Like you've got to be able to identify what those things mean. Okay, but your only actual solution is 9. Did that help with 11?
Do you just plug it back in to find out?
Yeah, you plug it back into the original problem. So like if we go back to the very original here, then I'm taking everything that was an x and I'm going to replace it with 4. I'll do that one because we know that's the one that's extraneous. So we get 4 equals 5 plus, okay, I am going to write that as the square root of 3 times 4 minus 11. So then that's 4 equals 5 plus, okay, what is 3 times 4? And 12 minus 11 is 1, the square root of 1. And the square root of 1 is 1, so I end up with 4 equals 5 plus 1. And what's 5 plus 1? Yeah. So I end up, like I said, with 4 equals 6. Well, that's not true. That's why 4 is extraneous. When you plug in 9, you do get the same thing on both. I think you get 9 on both sides, actually. Yeah, when you plug in 9, you actually end up with 9 on both sides. So, what else? I know. It's amazing how math works. It was. All right, 14. On your test, you do not have a problem. I can tell you this. You do not have a problem where you have a cube root and a square root. Like you will, if you have multiple roots, they'll both be the same. Okay? So there's none where they are different. But if they are, because I know that's like, what do you do if they're different? If they're different, you need to write them as exponents first. Because when we see them as exponents, then we can apply our exponent rules to that instead of like having to do anything else. So I'm going to rewrite this problem as x to the 8 over 3, y to the 7 over 3, because we can write radicals, we write roots as the denominators in our fractional exponents and our rational exponents. And then x to the 4 over 2, y to the 1/2. Okay, so when I'm dividing, what do I do with my exponents? Yes. So what is 8 over 3 minus 4 over 2? Or 8 over 3 minus 2? You would have to get a common denominator. You can also use a calculator to do the math. If you were going to get a common denominator, your common denominator would be 6. Actually, hold on. What is 4 over 2? 2. So now to get a common denominator, really that's 6 over 2, right? And 8 over 3 minus, or sorry, 6 over 3, wrong thing. I wrote the wrong thing. I think I said the wrong thing too. 6 over 3, there we go. So what is 8 over 3 minus 6 over 3? Yes. And again, you can use your calculator, like do 8 over 3 minus 4 over 2, or 8 over 3 minus 2. I promise it's going to give you the same thing. It's going to give you 2/3. And then same principle, if I am subtracting my exponent, 7/3 minus 1/2, again, a common denominator would be helpful. What would my common denominator here be? Yes. So this would really be 14 over 6, and this would be 3 over 6. So what is 14 over 6 minus 3 over 6?
11 over 6.
So this would be y to the 11 over 6 power. And again, I really, really, really want these to have common denominators. I can't combine them together, but I am going to be able to write these underneath one radical if they have the same denominator. So I'm going to change 2/3 to 4/6. 4/6. Is that what I said? Yeah, 4/6. And now I can write this as the 6th root of something. So it'd be the 6th root of what? X to the 4th, y to the 11th. Can I simplify that anymore?
Yes.
Yes, because I have this y to the 11th here. That means that I'm going to have a whole group of y's I can take out because I'm looking for groups of 6. I can't do anything with the x's. I only have 4 x's. So I can't group them up because I don't have 6. So, but I do have a group of y's. So I'm going to end up with how many groups of y's? 1 or 2? 1. And how many are left over? 5. So that's going to stay on the inside. That was really horribly written. Sorry. So 5 will be left over on the inside. I can't group up that x to the 4th, so it's going to stay there. So that would be my final answer. Here's your reference page for exponential functions. I need to just introduce some vocabulary to you that just so that you know like what things are. So I'm going to write some things up here in the top corner. I'm going to start with 3x squared, and I'm just reviewing, not really introducing vocabulary, it's more like reviewing vocabulary with you. In this problem that you have here, what is the 2? And this is an easy one. Yes, it's the exponent. Okay, what about the 3 that's here in front? Yes, it's the coefficient. That's a funny word to spell. And then lastly, we have our x here. And x is called our base. Anything that has an exponent attached to it is considered the base. That's important. I'm going to talk about the base a lot today. I need you to know what I'm referring to. Okay? So, I'm just addressing what that is now because we're going to reference the word base a lot. And you need to know that the good thing about exponential functions when it comes to transformation, it doesn't matter what your base is. The base has no bearing on the problem. We are not even concerned about that at all. So like if you look at your reference page here, notice we're only addressing 3 of our letters this time, 3 of our transformations. We are only worried about vertical stretches and compressions, horizontal shifts, and vertical shifts. That's it. We are not going to deal with horizontal stretches and compressions at all, which is really nice because of the 4 things, that one is by far the most difficult. It's not complicated, but it is the most complicated in comparison to everything else. So, again, we only focus on our vertical stretches and compressions. B doesn't matter. I will tell you, with what we're dealing with today, B, our base, that's what B is in this case. B represents our base. And it's going to be one of, in most problems, it is one of 3 things. It is either 2, or it is 10, or it is E. And this is the part that's going to be the weirdest for y'all, because you're like, wait, what's E? So no, it's actually not. E is like pi. Pi is a symbol that represents a specific number, right? 3.14159, so forth. E is the exact same thing. It's called the transcendental. I think it's called the transcendental number. Like, I'm 95% confident that's the name of it. It's a number. It's like 2.71 something, blah, 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 blah. And again, just like pi, and you don't want to write out all the digits of pi. You don't want to write out all the digits of E, so they use the letter E to represent it. So E is a variable, but it represents like a super specific number, just like pi. But you're not going to pay any attention to it. Again, it doesn't matter if your base is 2, if your base is 10, or if your base is E. It works the exact same every time. Okay? So look at the notes problems. The next I gave you, because I gave you 2. Yeah, it's a really long number. Yeah, so if I'm applying my transformations here, we have -3 times 2 to the x minus 2 plus 1. Okay, so let's start with the negative sign at the very front of the problem. What's that going to do? Reflect over the x-axis. And my Algebra 1 kids decided they were going to be super lazy, and they just started writing Rox and Roy for reflections. And I was like, I'm good with this. So I'm just going to start writing Rox and Roy instead of the whole reflect over x-axis thing. So reflect over x for the Rox, and then reflect over y. It's Roy. And then 3. What is that 3 going to do to the graph? Yes, vertical stretch by a factor of 3. Okay, do I pay any attention at all to my 2 here that's my base? No, I ignore that. It does not matter to my problem. I'm only focused on the transformation. So the -2 that's up there with x, what's that going to do? Okay. And then lastly, my +1 here. Yup. So there's all of my transformations. Now I just have to find my domain and range. And if you look at your reference page, it tells you what your domain is. What's your domain every time? All real numbers. And you can write that -infinity to +infinity. You can write that all real numbers, the double R. I don't really care. You can write it in interval notation. You just need to know that it's all real numbers. At 1. Why did it end up at 1? Yep, because we shifted it up 1. So normally it's at 0, but if we move it up or down, then like it's going to be something different, obviously. So that's going to give us our horizontal asymptote. So it comes from whatever our our vertical shift was, provides our horizontal asymptote. And then my range is either y's that are less than that number or y's that are greater than that number. It's one of those 2 things. You do have to put the horizontal asymptote. So either the range is going to be, the graph is going to be above our horizontal asymptote, or our graph is going to be below the horizontal asymptote. What do you think makes it go below the horizontal asymptote? Yeah, a reflection over, yes, was there a reflection over the x-axis? So it's going to be y's that are less than 1. That means the graph flipped over our horizontal asymptote. Do what? So can our graph be equal to horizontal asymptotes? There we go. That's why. So, yes, that's why. So because we cannot cross a horizontal asymptote, well, yeah. There's some loose interpretation there on that. But again, it doesn't matter if my base is 2, if my base is 10, or if my base is E. You've got problems of each type. So like even down here looking at problem 3 where my base is E. What is my vertical stretch or compression? 3, is that a vertical stretch or vertical compression? Okay, so vertical stretch of 3. Okay, what else happens to this graph? Left 1, so that plus 1 is going to move it left 1. And then the plus 4 is going to move it up 4. So we know, do what? E is just my base this time. It's just like if we treat it the same as if that was a 2 or a 10 or a 15 or a 500 billion, like we just ignore that information. That's it. It basically tells us the rate at which we're increasing is what it's doing. When we get more into what an exponential function is exactly, then that'll start to make sense to you. But for our transformations, we ignore that information. Yes, ma'am. We could. We wouldn't have any transformations. None of these have that, but like if on problem 6, the question was, what if there was no transformation? So just like, kind of just thinking through this, if this wasn't there, then on this problem, my horizontal asymptote would be at 0 because I didn't move it up or down at all. But when we move it up or down, that's when we start to transfer it to something different. So in problem 3, what would be our horizontal asymptote? 4. So we'd have a horizontal asymptote at y equals 4. And then that means my range is going to have something to do with that. Is the graph going to be above 4 or below 4? Why not below? There was no reflection there. And then my domain, that's simple because that's the same every time. Negative infinity is less than x, which is less than infinity. That's fine. You can totally write the double R for all real numbers.